So let's start this lecture with the center of mass. This is a brief review of the previous chapter, so you may have learned it in the first semester, but it is necessary to understand the center of mass. So let's start reviewing it. It will be very brief. So in general, if you have a rigid body, okay, it will have center of mass somewhere, not necessarily inside the rigid body. It could have center of mass outside, for example, like this object. Center of mass may lie here, but anyhow, given a rigid object, the motion, the general motion, can be understood as a translation of center of mass. So the center of mass moves, translation, and rotation about it. Okay. So in general, you have, for example, 3 degrees of freedom for this part here, and also 3 degrees of freedom for this part, which I have explained in the previous lecture. And if this is rigid body, then all the relative positions are fixed. So if you know the motion of the center of mass, then at least, for example, you can determine all the translational motion and the rotational motion about it, because the distance between any points between center of mass and that point is fixed. Okay. So knowing the center of mass motion, in fact, determines the whole motion of the object. So here we know that the center of mass is defined as R center of mass is equal to total mass times MIRI, where here I is ice particle, okay, with mass Mi. And here, for example, sigma Mi is total mass, okay. And in component, x center of mass, x and y and z, this expression can be decomposed into x and y and z coordinate. Let's see whether. Okay. Now, the total linear momentum, of course, is equal to pi sum of all momentum, and that should be given by MIVI. Okay, so that is the total momentum of the system, and that from the previous definition, this one is nothing but MV center of mass. Here we have used, for example, R was equal to the center of mass is equal to M time over MIRI sigma, And if you differentiate both sides, you have m v center of mass on the left, and you have m I v I, and that is defined to be total mass. So P, the total momentum, is given by the central mass momentum. Okay, so here the linear momentum of a system of particles is equal to the velocity of central mass multiplied with the total mass of the system. So and we are going to show that if a force acts, if a force, external force, acts on a rigid body here with center of mass, this effect of the external force is precisely as if it is acting on the center of mass. So it should write M A center of mass. Okay? But here only external forces apply. So let's prove this. Here it is proved. Okay, so here this expression is the force acting on ice particle. So Newton's second equation gives you P I dot P P is equal to M I R I, the ice momentum. I'm sorry, V dot is dt over the, so the Fi, but here the F is the total. Okay, double dot, sorry. But so it consists of the, as it is written here, the initial external. So Fi, just one index, is external force plus Fj is equal to 1 and Fij, where this one is internal particle, internal force between I and J. Okay, usually we written it as Fji, which is equal to F force acting on ice particle by J. Okay, so that is notation in our general physics. But here it is written as Fij, so it's in opposite direction. Okay, so this Fij is force acting on ice particle by J's particle. Okay, so the total force, if you add up here, if you add up all these particle force, then you have this equation here. Okay, from here, just sum over all ice particle. And here Fij is internal force, the force between I and J, and by action and reaction by third law, this they always satisfy Fij is equal to minus Ji. Okay, so force acting on the J's ice particle by J's particle is equal to minus force acting on J's particle by the ice particle. So if you add up all these things goes to 0. Okay, so you have this one. Okay, so you have, if you add up all the part force external, here this force with a single index is external force acting on ice particle is equal to P dot, which is equal to ma center of mass, because this one comes from P is equal to mv center of mass. So if you differentiate it, P dot, it should equal to ma center of mass, okay, which was equal to, of course, Pi. So you obtain this result here, which says that the total force acting on all the force acting on the rigid body is acting as if it is acting on the center of mass. So it is used to generate a translational acceleration of the center of mass. Okay, so that is the one point of the center of mass here. Okay, so if you have a particle here, and if you apply external forces here, then the effect of external force is accelerate the center of mass with acceleration a center of mass, which is equal to total mass m over f external. Okay, this is total external force. So that is also one of the consequences of the definition of center of mass. So here, let's summarize this. The acceleration of the center of mass of a system particle is the same as that of a single particle having a mass, equal mass of the total mass, and acting on the system of external forces. So external forces, if you apply external forces to a rigid body, its effect is coming to a central mass. Okay, so for example, consider a swarm of particles, many particles moving in uniform gravitational field, and Fi is mig, and the total force is equal to this one, where m is the total mass. Okay, so a central mass is g here. Okay, here you used in this, here you used g is equal to constant for all particles. Okay, so g is constant for all particles, and then g can be taken out of the summation, and this one gives you m, which is mg. Therefore a central, but this one according to previous result is like what? M a central mass. Okay, therefore a central mass is equal to g. So this is the same as the equation of a single particle of projectiles. Now in the special case when no external forces are acting on the system, okay, then of course Fi is 0, and that means Pi is a constant. Okay, so that is the linear momentum conservation. So, for example, we know that if there is an isolate system, suppose there are many particles inside. This is not rigid, but this is just isolate system. Means that there is no exchange of force or work with the environment. So the total force, of course, is 0, and then it means that for isolate system, the total linear momentum is conserved. Okay. And remember that in deriving this linear momentum conservation, the total momentum, total external, the first condition is the total external force vanishes, but also we have used Fij, which is equal to Fji, okay? Force minus the force acting on i's particle by j's particle is equal to minus, okay? So this is Newton's third law. Okay, so these two conditions, you use these two conditions. But for example, what happens, okay, so in the next slide I'll explain it. What next slide, next page tells you is that if there is electromagnetic field, then we know, for example, in the presence of magnetic field, if you calculate the magnetic field, the law of action and reaction does not hold. Okay, the magnetic forces between moving charges, they do not have action and reaction. So what happens to conservation law? So let me explain this. So first, let me give you some example where this Fij is not equal to Fji. Okay, so this one is apparent in magnetic field. Okay. For example, if the charged particle, suppose they are both positively charged. Let's assume always positively charged for this discussion, moving in opposite direction like this. Okay, so this is V. I'm sorry. Let me make it more clear. So moving in opposite direction. Just let's consider simple. If this is V1 and this is V2. Okay. Then we know that this one will create a magnetic field, and we know that the field created magnetic field is in this direction like this by right hand rule, and here so it is coming, they are both, we assume that they are both positively charged, and here so you have magnetic field going into the board. Okay, it's going into. So according to there is a C over Q, V cross B force, Lorentz force. So the Lorentz force in this case is equal to what? This is V cross B is going into the direction, so V going in. So by right hand rule, the Lorentz force acts like this. Okay, so that is the Lorentz force acting on particle 2 in the presence of a magnetic field created by particle 1. Okay, here also you can see this moving charge creates magnetic field also. Okay, and by right hand rule it's going like this. Okay, going into the direct board. So here you have a magnetic charge going into the board. Okay, so this magnetic field is magnetic field created by moving charge V1. This one is magnetic field created by moving in opposite direction, but it also by right hand rule going in. Okay, so here also you have F Lorentz force here. So that is Lorentz force acting on 1 due to this moving charge 2, and this one is F2. Here you see F1, the magnitude is the same, but the line of action of force is not, is not collinear. It's not along the same, or it's not along the same line here. What I mean is that here the line is along this direction, and here the line is along this direction. Okay, so in this case Newton's third law does not apply. Because we know that Newton's third law, they must have the same lines of force. For example, like central force. Okay, if there is gravitational field, they are attracting each other. The lines of force is the same here, but here the lines of are not different. Okay, so in this case, this one does not hold. That means that remember this term, Fij is non-zero because they are not canceling each other for each Fij. So in this case, even if there's no other forces, okay, if I just think of this as a isolate system, then the momentum conservation does not hold. Okay, so what is happening? So that is a question. Here, of course, I can take this system to be very large, and we know that F Lorentz force is proportional to 1 over r squared. So if you go far from this two particle, then you can always go to a region where F is Lorentz force is 0. Okay. Of course, I'm not considering QE, which is always central force and which always satisfy this one. Okay. So if I include this one, the electric field part, it will be automatically 0. Okay, but for magnetic force, this does not hold. Okay, so that is first example, and the more easy example is like this one. Okay, here F and F1 and F2, the magnitude is the same, but there are cases, for example, we can consider cases where even the magnitude is not the same for magnetic forces. So for example, if you have proton or a charge moving in this direction, let's call it V1, and another charge moving in this direction, V2, okay? Suppose they're the same charge here, positively charged. Now, the magnetic field created by the charge 1, according to the right-hand rule, gives you in this direction. But here, at this moment, the particle is along the line of this motion, and therefore B at position 2 is equal to 0. Therefore, F2 is equal to 0. Okay, the magnetic force Q over C V cross B is 0 because B itself is 0 because this charge is now at the point where this line of this motion of V1. Whereas for V2, or let's use this metaphor, it creates a magnetic field along this direction. So here it is coming out the magnetic field created by this one, okay? And therefore V cross B for this particle, okay, is coming out, and therefore the right hand rule. So here you have this one and this one, and the right hand rule, V cross B is this direction, okay? So magnetic Lorentz force is non-zero, where in this case, I'm sorry, F1, this is 1, so F1 is 0, in this case F1 is non-zero, but F2 is 0 because the magnetic field P2 itself is 0. Here P1 is non-zero. So obviously in this case, not only they are not just the same. One is here the magnitude at least was the same, but in this situation, the magnitude are even different. Okay. Then of course this one holds, and in this system also the the I mean the third row, the linear momentum conservation is not varied. Okay, even if you think of this an isolated system. So does it conclude that for a it is in contradiction with the statement, I mean the famous, the very established statement that for an isolated system and there is no external I mean exchange of force and or energy with the environment, the total momentum should be constant. But here total momentum is not constant because this term, remember this term, does not cancel. The pair between I and J force does not cancel. So the resolution of this inconsistency, of course, is not true. You know, let me just erase some part of it. So the apparent resolution of this is, of course, you have to consider the field itself. Okay, so the resolution of this situation is that when you have an isolated system of charged particle moving in any direction you want, then when you calculate the total momentum, okay, when you calculate the total momentum, you not only include particle momentum P, the definition of P, for example, in this, let's assume just for two particles is P1 plus P2, which is equal to M1 V1 plus M2 V2. But you also, so that let's call it just mechanical. Okay, you also have to consider a field. Here you have electric field and magnetic field, and we know that this one also carries momentum. Okay, now in electromagnetism you will learn, I'll just briefly give you the result, but the details we will learn in oops, what's wrong? The details will run in electromagnetism. Okay, so let's enlarge this for you to so that you can read it more. Okay, so okay, so now I'm back. So when you have a charged particle system, let's just consider only two, but it can the general statement generalized to any n particle system, but I'll consider two. So the mechanical momentum is equal to m1 v1 plus m2 v2, okay, which is equal to p1 plus p2. And the field, because this is charged particle, electric field and magnetic field will be created and affect each particle's motion. You have also P electromagnetic field, okay, which is where let me just give you the sketch. This is proportional to dV times, for example, E cross B. I think people realize what is this E cross P is called Poynting vector. So the bottom line is that the total momentum should be defined as P mechanical plus P electromagnetic field. Okay, so if you calculate all these things, then dt over dp is equal to 0. It means that dt over dp mechanical is opposite of this, and that is electromagnetic force is created electromagnetic force, and dt over dp em is minus f electromagnetic field. Okay, so this is a very complicated expression. I'm not going into details, but the result is that the mechanical the force, of course, this one is of course is this part here, f I j is non-zero part. Okay, but that is precisely compensated by the electromagnetic field, and this one is true. So total momentum is conserved. Okay, so for this isolated system, the total momentum is conserved. It is true for all the nth particle. So that is how this paradox is resolved, that you always have for an isolated system that the total momentum is conserved. Okay, if you also take into consideration the field momentum. Okay, so we learned in general physics that the electromagnetic field has not only energy, but it also have momentum, and it also has force. Okay, this force is electromagnetic pressure. Pressure is related to pressure, and this relation is famous. If it is energy, then it should satisfy PC, always PC. Okay, so then much for the isolate system and linear conservation, and let's go to the example. So I'm not very good at this using this one, but just bear with me. oops. Oh, okay. So the lecture has ended abruptly. So let's continue. Okay. So let's look at this example. So here, at some point in trajectory, a ballistic missile of M breaks into three segments of mass 3m each, and one of the segments, so missile originally, for example, let's call it V0, breaks into three segments. Okay, uh, one segment continues on with an initial velocity of 1/2 of the velocity. So one segment goes V0 over 2. Okay, so it was originally mass m. So it is m over 3. Okay, and then the second one, and the other two pieces go up at like angles with each other. So the others goes at right angles. Okay, so this, sorry. So let's erase this thing. So since mass is 1/3 at right angles with each other. Okay, so since this is an isolated system, you can use m momentum conservation, which is equal mass of three segments, as it is here. Okay, and V1, let's call it this segment V1 to be 2V0, and V2 and V3 are perpendicular. So V2, V3 is equal to 0. That is the condition. Okay. So put this into here, you get m V0 is equal to 3 over m V0 over 2 plus 3 m over 3 V2 plus m over 3 V3. And if you put this into here, you get 6 V0 is equal to 3 V2 plus V3. Okay, so here this one cancels with 2. Okay, so you have 2/5 V0 is equal to V2 plus V3. So now you have to use this. You have to use this one. So you square it, and it gives you 25 over 4 V0 squared should equal to what? Let's do it just V2 V2. So it has V2 squared plus V3 squared. Okay, since V.2 V23 is equal to 0, but they also go with the same speed, so that is going to be 2 V2 squared. Okay, therefore V2, which is the same as V3, should equal to 5 over 2 square root 2 here. Okay, so it becomes 8. Okay, so it is 5 over 2 square root 2 V0. Okay, So you can understand the results. Just a brief mention with geometrically, because you know that this v0 over 2, okay, and the only way that I'm sorry, this one the final sum of these, the sum of these should be what? Uh, 5 over 6 v0 is so here v2 plus v3 is equal to 2/5 v0. So 2/5 v0 should equal to v2 plus v3, but they are the same lengths. Okay, so the only way that these two vector can add, the same vector can add up, is this vector like this, because they are perpendicular and they are same lengths. So this is isosceles. Okay, so that is just geometrically you can just see that this one, so that has to go in this direction, and that is 45 degrees. So this one, it should be 5 v0 over 2 times cosine 45, which is equal to square root 2 over 2, so it's a 2 root 2 or 5 v0. Okay, and that is the same as this one. So that is if you just don't want to calculate these things, you can just see it geometrically, it immediately gives you this answer. Okay, so then much for the brief review. Now in this we start now with chapter 8. So in this section we'll just calculate some of the center of mass. Okay, so this is an exercise section, because you have to you must be able to calculate many quantities, center of mass, for example, and also the moment of inertia, and all these things is just basic quantities. And moment of inertia is also, of course, it's the same form, but this one is only squared. So it is quadruple. This is linear, and the moment of inertia is quadruple. So you must be able to calculate these things by yourself. So this isn't just going to be an exercise section. Okay, so this one we have just appeared in the first lecture. Okay, so x center of mass, y center of mass, and z center of mass. Okay, and the mass distribution can be linear or planar or a volume. Okay, so for each cases, let's do some exercise. So for continuous distribution, you have this one and this one and this one. For a discrete contribution, you have this one. Okay, we'll do some exercise with continuous distribution. So before doing that, just let's remind us of what is xm is total mass, okay, over low x dl for a line. Okay, this one is for area. Here S is area. For line dl, area ds. So for volume, it's going to be x center of mass is equal to m over rho x times dv. Okay, this volume and x center of mass is equal to m over rho x d a. Usually it's written as a, but here this s is this area. Okay, so we are going to calculate examples of center of mass, which is very important in the rigid body analysis. So let's start. Okay, so first thing we consider is that if the center of mass, if the object has some symmetry, then it is very easy actually to calculate the center of mass. Actually, you don't have to calculate it. If you have some symmetry, then you can immediately conclude that some of the center of mass coordinate can be calculated precisely without any practical calculation. So let's see. If a body possesses symmetry, it is possible to take advantage of the symmetry in locating the center of mass. So this is the first example. If the body possesses a plane of symmetry, this planar symmetry, then each particle mi has a mirror image of itself mi prime relative to the some plane. Then the center of mass lies in that plane. Okay, so here it is proved. So you have some plane here. Let's call it for convenience x y. Okay, so what is the mean that the object has some symmetry? Means that suppose I have this x line here. This is a plane of x in this direction. Okay, so you have some object here, and this planar symmetry guarantees that in opposite portion you have exactly the same mass distribution. So each mi has counterpart exactly at the same location, mi prime, which is exactly minus mi. That is the meaning of this planar symmetry. So you can calculate this. For example, in this case, G center of mass is as calculated here, mi plus mi prime. Okay, so mi means in the upper hemisphere, and mi prime means in the lower. So this is I prime, the object here, and then you have zi mi plus zi prime mi prime. Okay, but zi prime is precisely minus zi, and mi prime is exactly the same as mi. That is what is meant by the planar symmetry. Okay, so this gives you for each zi and mi, you have exactly minus gi times the same mi. So this is 0. Okay, so without any further calculation, you can conclude that if an object has planar symmetry, then this center of mass must lie at z equals 0 here. Okay, so the g center of mass is 0 because there's a precise, each of the upper mass contribution is precisely cancelled by the lower contribution. So you can see that the symmetry greatly simplifies in locating the center of mass. Okay, so let's for example do here as it is here. if you have a line of symmetry, what is the meaning of line symmetry? You have line symmetry here. Suppose that line symmetry is z-axis. How is mass distributed? So in physics, the best known example is rotational symmetry around this g-axis. Okay. So if you look at the xy section, then it is precisely a what? Circle. Okay. So in this case also, you see the x, for example, if you calculate x center of mass, then it is given by sigma mi times sigma xi mi. But you see, if you have, if I let's draw it. If you have a rotational symmetry, if you have xi here, precisely you also have minus xi, but it is symmetric, so if the mass contribution is mi, here mi prime is precisely minus mi, the same mi, but xi prime is equal to minus xi. Okay, so each xi is cancelled. Whenever you calculate it, you always have contribution this one. So this is also going to be 0. And y center of mass by the same token should be 0. Okay, if you have any contribution of y, okay, it will precisely have the contribution, the mirror of this has this one, like this. Okay, so y center of mass is also 0, even without calculating here. Okay, you see, you can just for fun, you can actually see that you can have a weaker line symmetry. It's not rotational, but somewhat weaker than a rotation. So that mass distribution would look like this. Okay, suppose you have a mass distribution like this, then you can always construct a rigid body where x center of mass and y center of mass is 0, means that it has z symmetry, but it's not rotation. And the thing, the method to do is following. If you have the mass point here, you also have mass point, so that it always cancel x contribution, and this one to cancel y contribution, you can have this one, and this also x to cancel x also here like this. Okay, so the whole body would look like this. Okay, so this one, if you calculate it, is x center of mass is going to be 0, y center of mass is going to be 0. Okay, so this is somewhat weaker than rotational symmetry, but somehow it is also gives you the center of mass should be at the origin here. Okay, where if you have a point symmetry, then it is rather obvious that you must have sphere like this. So for point symmetry, you must have spherical symmetry. Okay, in this case, x center of mass, y center of mass, z center of mass should be all 0. Okay. Now let's calculate hemisphere. Here, solid hemisphere. It means this is volume contribution. Okay, so you just go through this. Z center of mass Z center of mass is equal to rho dv and rho z dv, and here this is volume integration, so you have to multiply x, y, z integration, and since this is finite integral, the result is finite, the ordering does not matter. So you can choose any order you wish. You can do it z first, or you can do it y first and z, okay, because this is finite integration. So now, the best way of doing this is as is in here. So it is here you do the xy integration first, and then you just pile this along z direction. Okay, so you have here dz contribution, and here also dz contribution, and you just pile it up like this. Okay, so if you do calculate the arbitrary z here, and then just integrate from 0 to a. Okay, so here for this with dg, this section looks like this one, this section here, with what here, this radius is a squared minus z squared using Pythagoras rule, because this is z, this is a, so the cross section of this has radius here, so it has area of pi, we know a squared minus g squared, sorry, okay, and then you have here with dg. Okay, so you have here dv element here, and then you just pile it up along z direction. Okay, so it has low pi a squared dz dv here, so that, sorry, let me make it, dv is this one, and you just do integration along z direction. Okay, you pile small segment up. Okay, so that is best way of doing this. So actually it is 3 integration, but this integration from symmetry, okay, from symmetry you can consider disk here, okay, and then just pile up from z equals 0 to a, and that gives you, so this integral is very easy, so let me just skip it. And this integration, everyone knows that z cubed is 1/4 g fourth. Okay, so it gives you 8.3a, so it's somewhere in down here. Okay, it's intuitively true, because lower side has lower side, if you look at this here, this down here, because the lower side has more mass distribution. Okay, so it should be at least less lower than one half here, 1/2 a. So let's do the next example. And in this case, it is a hemispherical shell. So the previous one was volume, but in this case, this is a shell here. So this is empty inside. It is spherical shell, half spherical shell. Okay. So in this case also you have this cross section. If you look at this here, you have cross section. Okay, and it piles out like this, and this shell, you first calculate the shell mass of this shell, and then pile up along this direction. Okay, so here ds here, the area is this radius, which is what? 2 pi, this is r, okay? So 2 pi r dl, which is this is this one here, dl, okay? So it is a d theta, okay? And r here is what? R here is, this is a, this, I'm sorry, this is a, this is z, so it is square root a squared z squared minus a d theta, okay? Now the theta integration can be, since we are piling up along z direction, okay, so you have here ds is equal to 2 pi square root a squared minus r a d theta, and let's change it to z because we are piling up along z direction. So you have z is equal to a, here you see z is equal to a, this is theta, so a sine theta, okay, and dz is equal to a cosine theta d theta, which is a square root 1 minus, minus sine square theta d theta, which is equal to square root here a squared minus a squared sine square theta is z, okay, so this one d theta, okay, so a square minus g square d theta is g, so it is ds is in terms of pi, z, it is 2 pi a z dc, okay, so that is what is written here, 2 pi z a dz here. So this integration is very easy. Z is equal to what? 1/2, okay, z dz is 1/2, so it gives 1/2 a, okay, so the central mass is located at precisely half of this in this case, okay, because mass distribution I mean there's no heavy, it is not heavier in the lower side because this is mass is distributed around the shell here, okay, so in this case it turns out it is precisely 1/2 a. Now semicircle, let's calculate it for semicircle. So let's first make a blackboard. So what is it for semicircle? Okay, semicircle is, you have to first be clear about what is semicircle is this one. So this is again empty because this is a semicircle, and this is planar, of course. And then here, since you have to decide which integration doing in, so but this is anyhow just a circle in plane, so there's only one way of doing integration, and that is theta integration, okay, so dl here is a d theta, that is very not well known, and z here is a sine theta, okay, z here, so here again here you just integrate along this direction, okay, so z center of mass is equal to log d a d theta, and z here, so okay, you have here z, and this is theta, and this is a, so you must have z is equal to a sine theta, okay, so this is sine theta here. Now this integration is easy. So let's do it just it. 0 pi rho a d theta and 0 pi rho a sine theta a d theta, and this one cancels, and that is a also 1a cancels, and that should give you pi, and this one is 0 over pi times a sine theta, and that we know is 2, so therefore it must have 2a over pi. Okay, so it is somewhere this, since this one is 3.1, and that is here. In this case it is above 1/2 here. Okay, so in this case this is 1/2 a, but it is above 1/2 a somehow. Okay, so let's go to next example. The next example is semicircular lamina. So I may repeat an exercise, but just since this is, since we have begin this, let's just calculate. So what is semi? So it is semicircle, but now it is full. Okay, so it is planar motion. So planar distribution. Okay, so here by symmetry also the center of mass is here and around somewhere here. Okay, so let's do the calculation. You if you take this as z, then you have to decide the center of mass, z center of mass here. Okay, so z according to definition should equal to rho ds rho z ds, and here you just this is area integral. So the best way of doing this is also you just make consider a strip with dz and just pile up to the z integration like this. Okay, so here dA is what? ds is what? dz times this length, this strip, so that should equal to what? This one is a, this one is z, so that is what? Square root a squared minus g squared. So it should equal to this one. So it should equal to 2 times square root a squared minus g squared. Okay, so z is equal to rho, let's just cancel rho first, and ds we know is what? 1/2 pi a squared. This is the area of a half circle, and then you have, since we are going piling up along z direction, you have 0 to a times 2z times this one, square root a squared minus g squared dz. Okay, usually when you have this kind of thing, you try to do integration with sine theta or cosine theta, but just look at the integral before that. You see here z dz, 2z dz. What is it? 2z dz is dz squared. Okay, so it basically goes to 1/2 pi a squared times 0a square root a squared minus g squared dz squared. Okay, so if you take z squared as x, let's call it a squared x. Okay, then this integral becomes 1/2 pi a squared over, when z is equal to 0, z is equal to a, x is equal to 1, so 0, 1, square root, this one is a, is pointed out, pulled out, and 1 minus x dx. Okay, so it is equal to 1/2 pi a squared times a, and 1 minus x is what? Uh, 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 3 over 2, 1 minus x, 2/3, and minus from 0 to 1. Because if you differentiate it, you get 2 over 3 in front, and this gives you square root, and minus gives you minus. So this one, when 1 is equal to 1 is 0, and when x is equal to 1 is 0, when x is equal to 0, it is minus, so it's 3, 2. Okay, so if you put this thing here, you finally get what? 3 over 4 pi, and this one, you should have, sorry, I somewhere missed a. You should have a dz square a square. So you should have a cubed here. Okay, so 4 pi a. Okay, so yeah, when you have dz squared here, a square dx, you have in front, so here dz squared, it should give you a squared dx. Okay, so this gives you a cubed. Here you should have a cubed here. Okay, yeah, you have one a here, and dz squared gives you a cubed, so this gives you a factor of a, this gives you a squared, sorry, so it gives you, so anyhow you should have z should have a dimension of a. Okay, so 4a plus 3 pi. Okay, so that is for semicircular lamina. So here in the book, they have an exercise for this solid cone. Okay, but let's just, this thing actually can be done with the, so this exercise, the purpose of this is that with the variable density. So density varies like this. So this is a solid cone, and the density varies like this. So what is the center of mass? Where is the center of mass? Okay, so you have this solid cone here. So we are going to do it analytically. In the text, this is the numerical simulation is performed, but let's do it analytically. So this has rotational symmetry, obviously. Okay, so x center of mass, y center of mass is 0, and you want to calculate z center of mass, which is equal to z d m over m, total mass. And here the point is the law xyz is changing square root x squared plus y squared. And so from the symmetry, it's best to use just the polar and polar coordinate. Okay, so let's first calculate m. M is going to be equal to rho r dr d theta, which is the polar area element, times dz. Obviously, we are also going to pile up along z direction, and that is equal to rho itself is a function of r, so it is r squared times dr times d zeta dz, and z is from 0 to 1, and r, let's do the cross section here, okay, cross section, and then we just pi it up, okay. So the zeta here, this is rotational symmetry. So let's do it first, the d zeta integration. So if you look at from here, it's just a sphere here like this, okay, with a radius r, okay, but r changes from 0 to a as g also changes. So when you do integration around dr, here the relation is very simple. Let's call this angle as phi. It's not zeta, it's phi. It's just this fixed angle here. Then you must have here r squared dr. So the integral goes to 0 to here. R is what? R is z tangent set, tangent phi. Okay, z tangent phi. Okay. So this integration is independent of r and z, so 2 pi. And when you do integral at fixed here, radius r, you integrate from the radius r is from 0 to this distance is what? Z tangent phi. Okay. And then z from 0 to, let's call this line as z is equal to 1. Okay. So this integration is very easy. It gives you 2 pi. This one is what? 3 over 1 tangent cubed phi times this one is z, right? 1. 2 pi 3 over r cubed. I'm sorry. 3 over r cubed z cubed here. Z cubed here. So it gives you. So this one gives you. Sorry. This one gives 1 3 z cubed tangent square phi. Okay. So you have here z cubed dz1, so it gives you 1/4 here. Okay. Now rho, the numerator also can be calculated easily. So you see z dm, this is precisely the same except that you here have another factor z here, so it should give you 0 1 z dz, and the rest is the same, 0 to z tangent phi r squared dr, and 0 to pi d zeta. Okay, so that gives you 2 pi d zeta. 2 pi times this one is the same, so it gives you 1 cubed tangent square phi. Now here you have z cubed here, but another factor here, so it is 0 z fourth dz this time. So that gives you 2 pi 1/3 tangent cube, and then what? This is fifth one. You see? So the only thing has changed is because of this g factor, you have 1/4 and 1/5 here. Therefore, z, which is equal to this one over m, is what? these factors are all the same, and that is 1/5 over 1/4. That is 4/5, which is approximately 0.8. Okay. So you see there is some pattern here. If z increases by 2, if this z is equal to 1, but the cone extends to z equal to 2, the only factor matters here is this one. This will change what? Is this z cubed, so z force integral gives you this force, so it should give it 1/2. It should give you factor 16 here. Also, this also gives you factor 16, and you see how it changes here. Okay, if this extends, you have some pattern, because you only have to have this extra factor in z here. Okay, so anyhow, for this z height, z is equal to 1, the center of mass lies about 0.8 from the bottom. Okay, so the numerical result should also very much resemble this. Okay, so here x, y, z is equal to 0, 0, and 0.8, and 0.017. So this is 0.8. Okay, so the numerical computation has the error of this much, but the analytic result gives you 0.8.